So we're going to talk about this calorimetry lab. Half of you did this experiment on Tuesday. How many of you still have some questions about it? Right? There was a lot of math and equations, right? And then the Thursday people are doing that experiment today, and so you're going to have a lot of questions. So I'm going to go over it and record it so that if you want to, you can go back and hear the explanation again. Okay, so the idea here with calorimetry is we're just using styrofoam cups. Actually, they're nested, so 2 styrofoam cups. This is our calorimeter. The calorimeter is something that isolates, in this case, water from the environment, and so we can measure the changes in the temperature and the amount of heat that's transferred. So we've got our calorimeter, and what you're going to do, I'll talk about the actual experiment first and then the calibration. So what you're going to do is you're going to put some cold water in this calorimeter, and we're going to have an initial temperature. Let's say it's 22 degrees Celsius. You measure it with a thermometer, and you're going to know the mass of that water. So the mass of the water is going to be 50 grams. And then we know the specific heat capacity of water. So the specific heat for the water is 4.184 joules per gram degrees Celsius. And then we're going to have some metal pieces. I'll make them look like copper. We're going to stick, can you see that? That doesn't show up very well. Let's go with a lighter color. Okay, so you're gonna heat up some metal pieces, and so over here we've got our metal, and the initial temperature of the metal, because it's going to be sitting in a beaker of boiling water, it's going to be about 100 degrees Celsius. So I'm going to say it's exactly 100 degrees Celsius. So the metal was at 100 degrees Celsius to start out with, and the water was at 22 degrees Celsius. When I take that hot chunk of metal, we weighed that too, so maybe the mass of that is 27.43 grams. When we take that hot metal and put it into the cold water, what happens to the temperature of the water? It's going to go up, right? And what happens to the temperature of the metal? It's going to go down. And where are they going to end up relative to each other? They're going to get to an equilibrium. They're going to get to the same temperature. Remember, heat is the flow of energy driven by temperature change. So there's more energy in the hot metal, and that will flow into the cold water until they are both at the same temperature. So when we're all done, we measure the temperature of the water, and maybe we find that the final temperature is equal to, 58.4 degrees Celsius. What we're trying to figure out in this experiment is what is the specific heat capacity of the metal. Can we calculate how much energy was gained by the cold water? We can, because this final temperature applies to the metal and to the water. So the final temperature of the water is also 58.4 degrees Celsius. So we can use the equation Q equals mc delta T to find out how much energy was gained by the water. Well, delta T is going to be this 58 minus the 22. Q is going to be 50 grams times the specific heat of water and the change in temperature is 58.4 minus 22. So that's 36.4, right? So calculator says 50 times 4.184 times 36.4, 7,614 joules. 614.88 joules. That's how much energy was gained by the water. Where did that energy come from? It came from the metal, right? How much energy did the metal lose? The same amount that the water gained, right? We talked about the conservation of energy, that the energy content of the universe is constant. So Q for the water plus Q for the metal must be equal to 0. In this explanation, I am ignoring the fact that the calorimeter does absorb a little bit of energy. We're just ignoring that. We're not going to ignore it in lab, but we can ignore it in the classroom. So if this plus this equals 0, then Q metal must equal the negative of Q water, right? So then we know that Q metal equals minus 7614.88 joules. Oh, let's not ignore our sig figs. 3 sig figs, 4 sig figs, 3 sig figs. So this should only have 3. But we're not going to round it off till the very end. So we have Q, we have M, we have initial temperature, we have final temperature. What we're missing is the specific heat capacity, and that's what we're trying to find. And I don't have much space here. So I'm all done with the water, so I'm going to get rid of that. It'll be on YouTube if you want to go see it later. But I need the space. So Q equals MC delta T. This time we're trying to solve for C. I'm going to divide by M, and I'm going to divide by delta T. Those guys are going to cancel out. I have to do the same thing to the other side. So I end up with an equation that C equals Q divided by the mass times the change in temperature. The change in temperature is the final temperature minus the initial temperature. Is that going to be a positive number or a negative number? It's going to be a negative number because the temperature of the metal went down. That's negative. So delta T equals minus 41.6. .4, the final temperature, minus 100, the initial temperature, gets us minus 41.6. So here I'm going to put in my Q, minus 7614. I'm writing numbers, and what my mouth is saying has no relationship to what I'm writing. Maybe I should stop talking. And down here, M is 27.43. grams. And the change in temperature is minus 41.6 degrees Celsius. Look at the units. Do any of the units cancel? No. Is that bad? Doesn't have to be. It is what it is. So they're all just going to hang around. But let's do the math. 7614.88, make that a negative number. Divide by 27.43. Divide by 41.6 as a negative number. And we're going to get a positive number. I'm going to get 6.67335 joules over grams degrees Celsius. How many significant figures in the final answer? This one has how many? And this one has 4, and that one has 3. So we should round this off to 3, and we're going to say this is 6.67, and the units, joules per gram degrees Celsius. Reasonable values for specific heat, it has to be positive. Because if it's negative, that's impossible. A negative heat capacity would mean that if you put that object on the stove and put energy into it, it would get colder. Does that ever happen? No, it doesn't happen. There's got to be a positive number. If you've got a negative number there, something went wrong in your calculations. That number could be really small, like 0.1. If you end up with a number in your lab of like 5,000, something's wrong, most likely a calculation. This is obviously not a correct specific heat for copper metal, but that's because I just made up numbers without thinking about what the final answer would end up being. Any questions? The big idea for calorimetry is this right here. Everything that's changing temperature, the heat energy from each of those things, they all have to add up to 0. Some things are losing energy, some things are gaining energy. I think I forgot to tell you this in lecture, about the sign on energy. So if money is leaving your wallet, how do you feel about that? Positive or negative? Negative. And if money is coming into your wallet, how do you feel? Positive. It's the same thing with the energy. The chemical reaction that you're thinking about is like your wallet. And the energy is like money. If the energy is leaving, we say it's negative. And if energy is coming in, it's positive. So here for the metal, Q was negative because the metal was losing energy. Q for the water was positive because it was getting energy. That's like if I take $5 out of my wallet and give it to you. It's negative for me and positive for you. Same number, though. Okay? So there's calorimetry in a nutshell.